Hello everyone, do you hear me? Thank you very much. So we're ready to start this last lecture of the semester. So welcome to the course on distance vector routing. As this figure is illustrating, distance vector routing has an analogy with the way road traffic signs are used, as we will see in a few more minutes. We'll start with a theory and say a few words about the protocol, the most widespread protocol that implements distance vector routing, which is RIP. So distance vector routing is a method that is very simple in terms of footprint. It uses very little processing power and very little memory. So that's the method that was very much used in the past and is still used today in small networks, also because the protocols like RIP are largely plug and play. So what is distance vector? We have already discussed some aspects of it. So what it does is the same as link state. It computes shortest path to all destinations, where the cost of the path is given by the link cost that you have assigned by some configuration. Some protocols like RIP that I mentioned will give the same cost to every link, in which case the cost to a destination is simply the number of hops. But contrary to link state, it is using the distributed Bellman-Ford algorithm. That's for the technical part. But the main part is that the only information that is stored is the distances from self to all destinations. So the goal of a routing protocol is to compute the distances, but we have seen that routing protocols such as OSPF use a routing information base that contains the entire topology of the network, and only once they have the entire topology, they compute the distances to every destination. Here, we don't need the topology, we need only the distance to every destination. Originally, this was the information that was in the routing table. So in a simplest form, distance vector uses as only information the information that is in the routing table. This is no longer true of all distance vector routing protocols. Some use a separate data structure, but for very simple protocols, that is the idea. Then, how is that possible? Well, it's possible thanks to the Bellman-Ford algorithm that we will see in several passes. First, I will give a centralized version of the Bellman-Ford algorithm. So this is not what is used in distance vector routing, because in distance vector, the algorithm is distributed in all routers. But explaining it in the centralized form will allow us to understand how it works considerably more easily. This is a shortest path computation algorithm, so it's competing with Dijkstra, and it is not the best one in terms of performance, so that's not the one you would use in a centralized way, but it lends itself well to distribution. That's why we use it. If we would use it in a centralized way, for example, in a software-defined network context, we would have a central node that knows the costs of all the links. So here I'm assuming I represent the network as a graph that can be oriented. So the cost from I to J has a certain value, can be different than the reverse direction, although for many protocols it will be the same. And the goal of this code that I'm showing here is to compute the cost from anywhere to one specific node. This is the inverse of what we did with Dijkstra, where we computed the cost from self to every other node. Here we compute a vector, which is the cost of the best path from this node to node 1. So a vector, every node will compute just a scalar, just one value here. Of course, when we will use that in a network, we will need to do it for all possible destinations, but we will simply replicate the same computation in parallel for all possible destinations. So here I have a network where the node of interest is node 1, and we want to estimate in every node I what is the cost of going from node I to node 1. So it works as follows. Initial conditions, we set the distance of 1 to 1 equal to 0, because 1 is the destination. And for every other node, we set it to plus infinity, because we don't know anything at the beginning. Then we iterate, and at every iteration we do the following. The update of the best estimate of the cost from I to 1 is obtained by taking the values we had at the previous previous round of all the neighbors of I. So J is a potential neighbor of I, and we ask J, what was your value in the previous round? And we add the cost of going from I to J. And we take the minimum overall neighbors. Here I write overall J, not specifically neighbors, but that's the same because if J is not a neighbor, this A will be infinite and it will not show up in the min. And we force, of course, the value of 1 to always be 0. So we do that until, by some magic, we hope, it will become stationary. The new thing we compute is equal to the old one. When that happens, we exit and we have obtained, we think, the final values of the destination. So here's an example, a similar graph to what we had before, with the link costs here that are bidirectional are given here on the edges. And the node of interest is the node 1 here, and we want to have an estimate of the distance from any node to 1. So of course from 1 to 1 it's 0, that's written in the box here, and at the first round it is infinite for all others. Then if I zoom on node B, for example, B will, from the previous iteration, ask all the neighbors what were your values. Of course, all neighbors are not interested except 1. So we'll ask 1, what was your value? It is 0. My cost from B to 1 is 1, so my estimate is 1 here. D will do the same. D asks 1 what is its value and obtains an estimate of 5. The others stay with their initial estimate of plus infinity here. So this is an interpretation in a centralized way, but another alternative interpretation, which is interesting, is the so-called message passing interpretation. The message passing interpretation consists in saying, this is as if at iteration k, node I receives from every neighbor their previous costs and updates its own estimate by comparing to what it has received and taking the best of what it can obtain by comparing all those things, which is in reality what happens in distance vector. In distance vector routing protocols, the node will inform their neighbors of their own estimates of the costs, and the neighbors will use that to improve their things. So we can interpret that here in this way, except in the centralized interpretation, this happens synchronously. In one round, every node obtains from all neighbors all the costs that the neighbors had computed in the previous rounds. For example, here, this is illustrating what at the second iteration node E will do. E will obtain from its 3 neighbors C, B, and E their own values, which are given in yellow here, and will update its own estimate. So from D, which had a value of 5, 1 plus 5 gives a potential distance of 6. From B, which had a value of 1, 1 plus 2 give a potential value of 3, which is better. So I forget the D value and I obtain the B value. And from C, I obtain plus infinity, which of course is not better. So the update that is obtained by E is 3 here. So if we run this, we said 2 steps we did here, when do you think that the algorithm will stop, if it really stops? I close the poll in a few seconds. And the majority says D, which is indeed the correct answer. This is what we will obtain at the third iteration. We have those distances, and at the fourth one, the following one, they don't change anymore. So that is the final thing, the final step for this algorithm. An interesting thing to observe is that once we have the destination, the distances, we can deduce from that also the next hop to the destination. For example, node E not only computed its destination as being 3, but also it remembers that it obtained it by finding B as the best neighbor. Remember when I showed a few minutes ago the message passing interpretation, E had received from C, B and D updates, and the best one that it ever had was the update from B. So E can remember this and conclude from that that the path towards 1 is towards B. If E had forgotten, once E knows the values of the neighbors here, so in the last step, the step that has converged, you can do the same computation. E can compare the cost of going to 1 by comparing with the 3 possible neighbors, 2 plus 1, 1 plus 6, and 1 plus 5. The smallest is this one, so E will conclude that the next hop is B. So by knowing my own cost and remembering the previous information I had received from the neighbors, I can conclude what is the next hop. This is how, in a first approximation, distance vector works here. So I've illustrated this algorithm on an example. Of course, it's not just an illustration, but there is a theorem that I call the correctness of Bellman-Ford centralized, which says that if the network is fully connected, the algorithm will stop at the latest at the number of nodes and will output the distances along the shortest path from any nodes to node 1. And why does it do this? Well, it's very easy to understand, at least in this setting here. We can easily see that at iteration 0, the distances are the distance in 0 hop in k equal 1. And if we apply this here, we obtain the distance if we allow 1 hop. So that's the immediate neighbors. And by induction, it's easy to see that if pk minus 1 is the distance from I to 1, if we allow at most k minus 1 hops, then pk of I will be what we obtain if we allow at most k minus 1 hop plus 1, which is k hops. So the correctness proof is simply based on this, is that at iteration k, what we have is an expanding search where we obtain the distance from every node to 1 in at most k hops. Since the network is finite and fully connected, in at most a finite number of hops, it will converge to the distance. And as we said before, the next hop can also be obtained by comparing the distance to all that we obtain by going via any neighbor. So this I've already explained here. Now this is the easy part of the algorithm, but the reality is not exactly that one, because in reality, like we saw already with OSPF and BGP, the conditions are changing. So we will not run this algorithm, not necessarily with the initial conditions we had. So what happens if we change the initial conditions? So we run the same algorithm, but for some reason, the initial conditions are the ones shown on the graph. So 1 always believes it is at a distance of 0 to self, as obviously, but for some reason, B believes initially it is at the distance of 10, and D that it is at a distance of 1. Why could that happen? Well, it could happen in some circumstances because the network has changed. Perhaps D had another link to 1, which was at the cost of 1, and this link has gone down. And perhaps the link from B to 1 and from B to D have been newly installed. And before that, B had a link to 1, which was at the cost of 10. So whenever there are changes in the topology of the network, in the presence of links, failures of nodes, changes in the costs, then those values here that we have are not necessarily the initial condition. And the assumption is, or the question is, can we simply let the Bellman-Ford algorithm run asynchronously, or do we need to reset it? That's the question. Here, let's examine what happens if we do not reset it. What do you think that will happen? I close the poll in a few seconds. And the majority thinks C, which makes sense, but is not the truth. At least in this case, there is some magic that is happening. If we observe what happens, so we start with this wrong initial conditions, then we see, for example, that node D will speak to the neighbors, B and 1, and we'll get from B a very large value, 12, and from 1 a value of 5, and also from E a value of 1 plus 1, 2. So D will update it to 2 in the next step, which is incorrect. Well, we know the true value from D to 1 is, if we visually do it, we see 2 plus 1 is 3. 3 should be the final value. So this is incorrect here. Similarly, the value of E is incorrect. But we see that sooner or later, the D will continue asking the neighbors. The neighbors in between have changed their values. For example, the value of 2 that was due to E having a small value of 1 is no longer the one it will get, because E in the meantime did something similar to D. The value of D that was 1 has increased to 2, and similarly the value of E has also increased to 2. So at the next iteration, D will increase it, and eventually we see that it converges to values that are the correct one. So on this example, the algorithm converges to the correct value in spite of initial conditions that are completely abnormal. So let's try an even tougher example. Assume that the network becomes disconnected. So we have this node, this network here. We have those values that were the correct values before the failure, and assume we break all those links. Now, is it realistic to assume that 3 links can break at the same time? If you're optimistic, you will say no. But if you are more pessimistic, you say that can happen. And the reality, the sad reality is that it can happen, for example, because those 3 links have something in common, which may be a digital cross-connect, which may be stupid infrastructure. For example, they use cables that are buried in the same conduit, and there was construction works, and construction works broke this conduit, for example. So this could happen, and if this happens, are we able to continue to run Bellman-Ford, or should we reset the network? So same question, what will happen here? I close in a few seconds. And the majority says A, which unfortunately would be nice, but, or in some sense is true, but let's see exactly what happens. So this is the starting condition. Then we see that C will ask E, what is your distance? E will say 3. C will say, okay, I have 4, 3 plus 4, no better, I stay with 4. E will ask C, and C will say, I am 4. Okay, E had 3, but nothing else, so E will say, I am 5 now. Then C will ask E, and E says 5, therefore C concludes 6. Then E asks C and concludes 7, then C asks A and concludes 8. We see that on this example, what will happen is a ping-pong game between C and E. Remember, that's the distance to node 1. So the true value of the distance is plus infinity. So the algorithm is in fact computing the true value. It is counting to infinity. But in some sense, it does not converge. The algorithm will never stop. But it's doing the right thing. It's going to infinity. And in the other part of the network, well, which is not affected by the cut, the algorithm stays where it is, so it does compute the correct value. So there is some magic about Bellman-Ford with arbitrary initial conditions. And the magic is that it continues to do the best possible thing and compute either the correct value if the network is connected, or it will count to infinity if the network is not connected, whatever the initial conditions. This whatever is very important. So if there is a path from I to 1, then for k large enough, k is the iteration count, the value will become the true distance to the final destination here. So if the network is fully connected with arbitrary initial conditions, it will work. However, we have lost, in this case, the interpretation that when k is small, we have the distance after in at most k hops. This is true only with the initial conditions that I gave initially. But if we have arbitrary initial conditions, that will happen. And then if there is no path from I to the destination, then it will count to infinity. So what happens is exactly what we have seen in this example here, is that the algorithm increases the value until the values are large enough, and then it's as if it would be with the initial conditions infinite, which would be the regular initial conditions. The proof is in the lecture note because it's not easy to find. Usually textbooks on Bellman-Ford just use the good initial conditions, but the reality is we will not have the good initial conditions. So that's the major thing that makes Bellman-Ford work. Because if we change the initial conditions, that's very similar to what happens if we distribute Bellman-Ford. So Bellman-Ford can be used in a centralized way in the following way. So that's a preliminary version. That's not the one you find in most distance vector routing protocols. Some do it, but most don't. I call it, therefore, Bellman-Ford prelim. So, because if you remember, what Bellman-Ford does is ask the neighbor, what is, I am node I ask all my neighbors J, what is your estimate? And I compare the best of what I get from my neighbor's estimate. So the only thing I need to do, if I want to do it locally, is to remember the estimates of my neighbors. So node I maintains an estimate of the estimates of the neighbors and of its own estimate. And whenever, from time to time, it will send a message to all neighbors. That's the message passing interpretation, which is now a true implementation. There's just an interpretation. Therefore, all neighbors will do the same. And once in a while, I will receive from neighbor J an update. And then I will compare what I had, my best estimate, to what I can do if I use this update. If I go via neighbor J, the cost that I will have is the cost of going to J plus the cost from J to the final destination. And I compare that over the values I have for all neighbors, and that's the best value I have and the value I keep. And that's the value I will send also to my neighbors when I send the next message. And for routing, I compute the next hop to I by looking for a value that achieves the mean in this equation here. So this is now the same as before, but we allow the message passing to be asynchronous. We have no concept of rounds. Some nodes may be faster, some updates may come one by one, and not all updates from the previous rounds, like in the centralized version we have. Then the important thing is that if we do this, it works the same way as before. It works as if it would be centralized. Of course, for this, you need to assume that eventually the messages do reach the neighbors. If one node takes an infinite time to send its update to a neighbor, of course, the thing will not work. So if we assume that every message takes at most capital T time units, or more precisely, if it takes at most capital T time units to reliably send to all neighbors the messages, then in a finite number, multiple of T, the network will converge as if it would be centralized. And perhaps, well, we'll not do the proof of that, but one way to understand this is that what happens when we do this is it is as if every node was doing the computation with initial conditions that are not necessarily synchronized, that don't necessarily make sense. So if it works regardless of the initial condition, it's not surprising that this distributed version also works. So here is an illustration. Here I'm assuming a starting point where I'm focusing on node E. Node E has an estimate of its distance to 1 equal to 4, and node E remembers the estimates it has received from the neighbors, which are C, B, and D. So from B there was nothing received, so it sets it to infinity. Then whenever B receives a message, E receives a message from B, because eventually B will compute that it is at the distance of 1, what does E do? Well, it compares the cost of going through all the neighbors, and it updates the latest received value. It compares the cost of going through all the neighbors and find a new value of 3, update its own value, and sooner or later will also send this information to all of its neighbors, which will allow the algorithm to converge. So ultimately, through this message received from E, C will update its value also to the correct value 4. Voilà. So this is distributed Bellman-Ford, and this is really the main part to remember. This is how it works well, and you can easily understand that this is hard to make to work with Dijkstra algorithms. So this is why we use Bellman-Ford. But by doing that, we don't exactly fulfill the job that I mentioned before, which is that the only routing information, that we have essentially no routing information base, that the only information we need for computing the shortest path is the routing table. Now, it's not exactly true, because in the information I gave, I need to remember not just my estimates to the destination, which is what is in my routing table, but also the estimates I have received from all neighbors. So if we want to remove that, then we can improve it with a super duper version of the algorithm that would do the following. I keep only my estimate, and whenever a neighbor gives to me an updated estimate, I recompute what I had by comparing what I had before with what I can deduce from what I have. If neighbor J gives me this value, I see here is the cost I will have if I go via J. Here's the cost I knew before. I take the best, and therefore that does the job, because the only thing I need to keep in memory is my estimate. Does this work? I close the poll in a few seconds. And the majority says B, which now is the correct answer. Congratulations. So super duper can only decrease the value. It can only improve. We always compare to what we have to something that is potentially better. So we have no way of increasing the value. If we start from initial conditions that were incorrect, like we saw a few minutes ago, that were below the initial value, we've seen that centralized Bellman-Ford and also the decentralized Bellman-Ford that is not super duper will converge to the correct condition. But here it's impossible, because it can only decrease. So if we start with values that are smaller than the final values, the algorithm gets stuck and cannot converge to the true value. With some work, it's possible to show that it will work if all initial conditions are above the final values. So for example, if you take infinity for all nodes except the final destination, it will work. But even then, we would not like to have such an implementation, because it means that if there is any change in the network conditions, the algorithm needs to be reset, right? So if we use this algorithm, we need a reset mechanism, which is a major pain in a distributed setting in a network. We would not like to have a global synchronization of all the nodes, because we know perhaps from distributed systems theory that achieving this with reliability is a very difficult thing, and the potential time is unbounded. So we would not like to have this. So instead, we would like an algorithm that converges even if the conditions change, and we continue from values that made sense in a previous setting, but are now incompatible with those kinds of conditions. So the super duper is not so super duper, and it's not the one that is implemented in most distance vector routing protocols. For this, we need to update to add a little trick. So the true version of the distributed Bellman-Ford algorithm is this one. As before, we keep an estimate of our roam distance to the node of interest. Of course, we remember the best neighbor next hop. This is because this is information that is in the routing table. The initial conditions can be anything, and from time to time, we send our value to the neighbors. Therefore, we also receive our values from neighbors. And when we receive a value from a neighbor, we do the following test. If this neighbor is a next hop, is on the shortest path to the destination, I adopt this value. So if j says to me, I have a distance which is q of j, and if before that I thought that going to the destination meant for me going through j, then I will update this, even if this gives a larger value. So if j has observed something that makes the distance become larger, I will adopt it. Otherwise, if j is not the next hop, I will do the same thing as before here. So we see that we allow here some escape that allows the values to increase. So perhaps there's a chance that it works, and the theorem says that, yes, if we do this change here, this will do exactly the same as the previous version of the distributed Bellman-Ford, the one that was correct here. So let's see an example. Here we zoom again on node C, right? The table shows the successive values of q of I and the next hop. So we need here just the distance. So E believes it is at a distance of 1, but also it believes the next hop is E, perhaps because C was giving a distance of 0 or whatever. Then when E receives from C a message saying my distance is 1, then E will accept it because it's the next hop and will force its value to be 2 here. And sooner or later, because this value was allowed to become 2 here, if we do the computations, we will see that all nodes, for example, node C, that was also thinking that the best hop is E, which was, of course, not such a good idea, will also increase its value. So even though we start from initial conditions that were too small for allowing the algorithm to converge, we will eventually increase them, and eventually we will converge to the correct conditions. As I mentioned, this algorithm can be proven to be giving the correct final value. Of course, we need, like before, to assume that eventually messages sent to neighbors will reach the neighbors in a time that is bounded, and if that happens, the algorithm will converge to the final conditions that we expect. So we have seen the theory that underlies distance vector routing. The distributed version of Bellman-Ford allows a node to compute distances to one destination by storing only the next hop and distance to destination here. And it works by message passing. Every node informs its neighbors of its current distance. And of course, as expected for a routing protocol, it is robust to initial conditions, and it does not need any reset, which means that it can continue to work asynchronously as desired in such a network. If a destination is unreachable, the algorithm still has the perhaps problematic property that it counts to infinity. So in practice, you will need to do something about it because you don't want to have an algorithm that continues forever increasing its value until there is an overflow. So let's see in practice how this is implemented in RIP. RIP is perhaps the oldest of the routing protocol. And that's the one that comes by default in all Linux and other operating systems, and is very, as I said, very small footprint, and is plug and play, because by default we don't need to give any cost. It gives a cost of 1. So RIP will do exactly what we said, except of course we do it for all possible destinations. So we run Bellman-Ford not just for node number 1, but for all possible destination prefixes here. So initially, node I will say that the cost of going to a prefix n is 1 if it's one of my if it's a prefix that is on one of my interfaces. Otherwise, I set it to infinity, and then I will do what we said before. I will send to my neighbors all my estimates, which is called the distance vector, because it's a vector, a list that contains all my estimates of the distances to all destinations. So all nodes will exchange with each other their own routing table, if you want. With RIP, updates are sent periodically, so this is not like BGP, right? Which means that if something happens, it might take a long time to converge. So RIP is not a high technology protocol, it's just a low-key protocol that will do the routing at very low cost, but also not very responsively. If a neighbor router doesn't work anymore, then, as usual, the absence of updates will mean that we will detect this as a loss. And for example, if the neighbor K is detected by node I as being dead, the node I will do the same as if it had received from node K the information that it is at an infinite distance to all nodes. And then we will rerun Bellman-Ford based on that. So it follows that if K was the next hop to the destination, then I declares the final destination unreachable, because remember, distributed Bellman-Ford adopts whatever decision comes from the next hop without comparing to the others. Let's see a small example on this network that is a loop with 4 nodes. This is the original values here. So there is no topology database. Everything we have is just the routing table. Node A, for example, knows that it has 2 directly connected prefixes, N1 and N4, and the distance is 1 on the next hop itself, of course. And similar for all nodes, with B, C, and D have other directly attached prefixes here. A will inform B, for example, of its distance to N1 and N4. For N1, it's not very interesting, but for N4, that's new information for B. So B will run Bellman-Ford. Before it had a distance of infinity to N4. Now it gets 1 information that is not from the next hop, of course, because it did not exist in its routing base. So it will compare to the existing, which was infinite, so it adopts it, and now it thinks it is at the distance of 2 of N4. D will do similar thing, and now D discovers N4 and M3 with distances. Eventually, C, for example, will also inform B of its distance to M3, for example, and B will use this to declare that it is at this distance 3 of M3 here. Eventually, all nodes will know of all the prefixes and will compute at least one shortest path. In this version, I'm assuming that there's only one shortest path, which makes the description simpler, but as with OSPF, it's possible to have multiple next hops, but I will not go through that in this presentation. Now, of course, what is interesting to check is what happens when the topology changes, for example, due to failures. So assume here A crashes. Then what will happen is that B will detect through the hello mechanism or BFD or other mechanisms that A is no longer present. If there's a direct Ethernet cable between A and B, then the interface at B will see that the cable is no longer operational, so that will be more immediate. Otherwise, we've seen in OSPF the BFD protocol with some routers send every 10 milliseconds a packet to all neighbors, or otherwise the absence of the hello protocol from RIP. Therefore, B will time out all the values that have A as next hop in its routing information base, and D will do the same. So they will delete them. And when, for example, D will receive an update from C, so here I'm assuming that C, of course, has not detected this, so D will receive from C an update that contains information, for example, from N1. So D has lost the path from N1 because it was through A, but C had one. So D will update it and we'll find now a distance of 3, which in this case is the correct distance here. Similarly, B will receive an update eventually from C to N4 and we'll find a distance of 3, which is also correct here. So in this example, we see that everything is perfect. Now let me take another example. The network is 1 iota more complicated. I have 5 nodes and I have destinations that are written here in small cap letters. And assume after convergence, this is the information we have. So all link costs are equal to 1. So for example, in order to go to destination C, A goes to next hop B, and the distance is 3 here. So the next hop here, which is written in the form of the link, the interface L1 here, in this case. Assume for some reason those 2 links break. For the same reason as I said before, we cut some plastic conduit in which those cables were put, for example. What will happen? Well, some of the nodes will detect it, perhaps not all at the same time, because all of this is asynchronous. So I'm assuming here D detects first that the neighbor E is no longer present, so it will declare that the distance C and E are non-reachable and that the cost is infinite here. Right. A little later, A will do the same. And now let's zoom on what, by accident, assume that A was just sending an update to D that was an update from before the failure. Right? Since everything is asynchronous, this message is in the pipe, is in transmission. A will take some time anyhow to detect the failure, so this is quite a possible scenario. Now D will use this information, which of course is incorrect. It's information from before the failure, and will think that it has those distances, that those prefixes, which in reality are not reachable, because they are in the other part of the network, for example, little c is not reachable, it will think that it's a distance of 4. But of course, sooner or later, A will detect the failure and will set it to infinity, but then A will receive from D an information that, for example, the prefix C is at a distance of 4. This is wrong, because if we go back, we see that this is originating from old information from A that was processed by D and sent back to A. But if we run asynchronously Bellman-Ford, this might happen. No worry, we see things Bellman-Ford work. So what will happen in this example? So what, for example, will be the distance at D to node E after processing the update shown in the figure? I close in a few seconds. tie between D and F, and the correct answer is F. What will happen here is the rules of Bellman-Ford distributed. Oops. The rules of Bellman-Ford distributed here says that D, so to destination prefix little e, the next hop is A. The interface is L3. So if I receive an update from the next hop, I adopt it. So D will adopt it, and A is saying I am a distance of 5. So D will say now I am at a distance of 6. So this is exactly what Bellman-Ford will do. Of course, this is what we've seen here. Of course, now D will send its information to A, which will cause A to calculate a distance of 7, which will eventually cause E to compute a distance of 8. We repeat here exactly what we saw a few minutes ago. When the network is partitioned, we know that the true distance is infinity, and distributed Bellman-Ford, if we do the correct version of distributed Bellman-Ford, will converge to the true, will do the right thing, which in that case means it will diverge to plus infinity, which is the correct distance. So here we have what is called count to infinity, which is a bit embarrassing. Here we need a way to stop that in a real network. Here we see that the costs grow unbounded, which is the expected behavior. So RIP, as you can imagine, is a very simplistic protocol. That's the beauty of simplicity. That's why also it's very efficient. It simply says, well, we set infinity to 16. RIP is for small networks. Small networks, if you have a number of hops larger than 16, then RIP might have problems. But if you have a not too large network, the default setting of RIP will simply say that. So RIP will do this count to infinity, but after, when it reaches the value of 16, it will say, well, that's enough. Those destinations are not reachable because for me, RIP 16 is a huge number that should never occur. Voila, we'll do a break and continue discussing how to improve this undesired behavior after the break.